I'm Ari Juels. My main affiliations are with Cornell Tech and the Initiative for Cryptocurrencies and Contracts. But I want to mention that this work was done in my separate capacity as a technical advisor to Chainlink. I'm going to talk today about mixicles. The term mixicle is a portmanteau word. It's a combination of the words mixers and oracles. And you'll see momentarily the rationale for this term. As of a couple of weeks ago, DeFi passed the billion-dollar mark. That's to say there's over $1 billion of cryptocurrency in DeFi smart contracts today. This is great, but wait just a minute. Should we know this? If DeFi transactions were private, we would only perhaps have a rough estimate of the amount of money in DeFi smart contracts today. But in fact, every single DeFi transaction is fully visible on-chain. There is no confidentiality. Additionally, DeFi smart contracts provide fairly esoteric, exotic, niche instruments. For instance, MakerDAO is basically an automated pawn shop for cryptocurrency, which you can use to achieve leveraged exposure and so on and so forth. And then there are flash loans that are used mainly just to weaponize idle cryptocurrency. Our goal with mixicles is to implement a fairly natural and common class of financial instruments, which includes things like simple binary options. A binary option is effectively a bet engaged in by two players, like our canonical Alice and Bob, who send money into a smart contract, for instance, and they are betting on an event with two different outcomes. So for example, they may bet on whether the value of a particular stock reaches a certain threshold, say XYZ reaches $300 at a particular time. And if the bet goes one way, for instance, if it turns out that this threshold is reached, then one player gets the money. And if it goes the other way, the other player gets the money. Right? Very simple and natural financial instrument. Our goals with mixicles in particular are four. The first is that we would like to achieve the type of confidentiality that, as I mentioned, isn't available in DeFi instruments today. And we're going to work in a particular model. We're going to assume that Alice and Bob are fine being recognized as trading partners. They might be financial institutions, in which case it's perfectly natural for them to work together, or they may have anonymized sufficiently the pseudonyms with which they're interacting or through which they're interacting with the DeFi instrument, so they're okay being recognized through these pseudonyms as trading partners. What we're interested in doing is concealing the type of trade they're engaging in and the payout amounts, how much money is involved to a certain extent. We want this thing to be auditable. It'd be very nice if there's an on-chain record available to third parties, auditors, regulators, and so on and so forth. We want compatibility with existing infrastructure. We would like to avoid having to build extra infrastructure specifically for our mixicles. I'll describe an alternative scheme that requires extra infrastructure. The main objective, though, in mixicles is simplicity. We're aiming for conceptual simplicity. As you'll see, mixicles are very simple from a conceptual standpoint. And conceptual simplicity often translates into simple implementation. And I'll give some evidence that the implementation itself was fairly simple to achieve. So in particular, we avoid heavyweight cryptography, zero-knowledge proofs, for instance. We avoid the need for watchtowers. And complexity is, of course, the enemy of security. Zcash, for example, had a bug in which, in principle, somebody could have minted an arbitrary amount of money without detection. And I would allege that that's in part because of the cryptographic complexity in Zcash's design. We avoid that in mixicles. I'm going to show you how to build a mixicle incrementally in 4 steps. The first thing we're going to achieve is payee privacy, because we're going to conceal which of the two players, Alice or Bob, has won the bet. Then I'll show you how to achieve trigger privacy. the trigger being the basis for the bet. For instance, the particular stock that Alice and Bob are betting on. Then we'll proceed to payout privacy, concealing, at least partially, the amount of money that's being paid out to one of the players. And finally, I'll show you how we can use multiple rounds to completely conceal intermediate payouts in the case where Alice and Bob are engaging in multiple transactions with one another. The starting point for the construction is a mixer. Mixers are used to conceal the flow of money in a cryptocurrency system by directing money to two different pseudonyms corresponding to the two players that have engaged in the mixer, if two players are involved. These pseudonyms correspond to Alice and Bob, but their order is randomized. Let me be a little bit more concrete. To perform the action of mixing, what Alice and Bob can do is very simply flip a coin. If the coin comes up heads, then the first pseudonym, P0, is allocated to Alice, or Alice's pseudonym comes first when money is output by the mixer, and Bob comes second. And of course, if the coin flip goes the other way, then the first pseudonym corresponds to Bob and the second to Alice. With this very simple construction protocol, we get payee privacy, our first goal for a mixicle. In particular, suppose that one of these two players sends money to some subversive organization. Anyone looking at this process on-chain will be unable to tell whether it was Alice or Bob who sent the money. That's the sense in which we get payee privacy. You can build a mixer very straightforwardly using a smart contract. Alice and Bob choose some pseudonyms off-chain. They flip a coin to determine how these pseudonyms get assigned to the players, in particular the ordering of the pseudonyms. The coin comes up heads, then the first pseudonym is Alice's, second pseudonym is Bob's. They commit their pseudonyms to the smart contract, then they send money into the smart contract, and the smart contract very simply forwards the money to the corresponding pseudonyms. Okay. We can take this basic construction and enhance it in various ways to achieve other goals. For example, suppose we want to do private payee gambling. Well, in that case, the mixer can take as additional input another coin flip, the result of flipping a public coin, or taking input generated by the blockchain into the smart contract. And then payment can be determined based on the coin flip. So if the coin comes up heads, the money goes to the first pseudonym, and if it comes up heads, goes to the second. You'll see we have payee privacy here. The identity of the winner is hidden on-chain, which is very nice. Now, of course, everyone's favorite place to gamble is the stock market. Right? We can transform this gambling smart contract into a financial instrument, one based on a stock ticker, for instance, fairly straightforwardly. Right? The smart contract simply takes as input an indication of whether the target stock, the stock that Alice and Bob are betting on in our binary option, has gone up or down. If it goes up, then of course the first pseudonym gets the money, and if it goes down, then the money is allocated to the second pseudonym. Right, this is the goal. There's a little complication, though. And you heard about this complication in the previous talk if you were here. The complication is that blockchains in general, and therefore smart contracts, don't have internet connections. This is a function of their underlying consensus protocols. That's to say that a smart contract can't do what you or I would do if we wanted to know the price of Tesla stock, namely just go to some trustworthy website and look it up. The solution to this problem, as you also heard during the last talk, is a piece of middleware known as an oracle. The job of an oracle, and this is an off-chain entity, is to go fetch data from a trustworthy website and push it on-chain, deliver it to a smart contract. If a smart contract needs to know a particular piece of data, it can call the Oracle on-chain. Oracle has an on-chain front end, and the Oracle will go out and fetch it and then relay it to the smart contract. So we can, in fact, realize the financial instrument I described before simply by engaging the services of an Oracle to indicate whether or not the target stock price went up or down, very simply. Okay. This is all well and good, but we still have a confidentiality problem here, right? If the Oracle is relaying the fact that a particular stock price moved in a particular direction, this is going to be visible on-chain. And that means that the basis of Alice and Bob's bet, the trigger, is world-readable, visible to everyone. And this we would like to avoid. We would like to achieve trigger privacy, as I described it earlier. How do we do this? Well, very simply, Alice and Bob can flip another secret coin, which they make visible to the Oracle. The purpose of this coin is to designate what I'll call a secret trigger code. If the coin comes up heads, then the Oracle, in the case that Tesla goes down, which means that Alice wins, is going to relay a 0 bit. And if the opposite occurs, it will relay a 1 bit. If the coin flip, on the other hand, is not heads but tails, then the code is inverted, right? In that case, B equals 0 corresponds to Bob winning, Tesla up in this case, and vice versa. So now, all that the Oracle is going to deliver to the smart contract is a single bit. And the meaning of the bit is randomized. Right? So now, it is not clear to somebody observing this process what it is that Alice and Bob bet on. In other words, we've concealed the trigger and achieved trigger privacy. So now we have both payee privacy and trigger privacy. This is great, but we're not quite there yet. We still have a confidentiality problem. Visible on-chain at this point is the amount of money paid to the winner. Everyone can see that the winner wins $1 in this particular case. And this, too, we would like, ideally, to conceal, at least partially. How do we do this? How do we achieve what I described earlier as payout privacy? It's easiest to explain payout privacy by example. Right? Rather than having Alice and Bob each pay in $1 and then sending all the money to the winner, what we can do instead is have them pay in $2 apiece and send $1 each to 4 different pseudonyms. In the case that the bid is 0, we'll send to pseudonyms P0 through P3. And in the case that the bid is a 1, we'll send the money to 4 different pseudonyms, P4 through P7. The key observation here is the following. Suppose that 3 of the pseudonyms correspond to Alice and 1 of them to Bob. Well, in this case, Alice wins $1. But if all of the pseudonyms belong to Alice, then Alice wins $2. And you'll notice there's no way for somebody just seeing dollars sent to 4 different pseudonyms to distinguish between these 2 cases. You can't tell if Alice is winning $1 or $2. And conversely, if 3 of the pseudonyms correspond to Bob and only 1 to Alice, then Alice loses $1. The upshot of all of this is that you can't tell by observing payment on-chain whether Alice lost $2, lost $1, whether neither of them lost anything, neither of the players, or she gained $1 or $2. In other words, we can conceal 5 different possible payment amounts for each player with this setup. And so we get at least partial payout privacy. We can amplify the privacy we achieve with a simple trick. The trick is to express the payment amount in binary and to allocate payments according to each of the digits of the binary string indicating the total payout. So for example, we can have payout amounts of $1, $2, $4, and, well, there's a little rounding issue with the last digit, $7 instead of $8. And now there are 29 different possibilities for the payouts allocated to players. To put it another way, the number of possible payouts now can be exponential in the number of actual payouts, whereas previously we needed a number of payouts linear in the total payout amount. So we get this nice amplification with this simple trick. With this now, we've achieved payee privacy, trigger privacy, and payout privacy. The final evolution of the Mixicle is use of multiple rounds, as I mentioned before. So in our initial setup, the players send some money into a smart contract, Oracle delivers its bit, and then one of the players gets paid, a payment is made to the pseudonyms, the payout occurs. But an alternative setup, and this is what we do if we have multiple rounds, is to keep the money in the smart contract and merely store in the smart contract a commitment to the balances of the players. As the players are not immediately receiving money, but their balances are recorded in a hidden way within the smart contract. And we can do this repeatedly. If Alice and Bob are going to engage in multiple interactions, we can continue to receive Oracle reports and update the secret state in the contract until the point at which the players decide that they want a payout to occur. And we can also make small modifications. Players can pay in money during intermediate rounds and can withdraw money during intermediate rounds as well, as you can imagine. What do we get from this arrangement? Well, we get an efficiency gain, which I'll describe a little later, but we also fully conceal intermediate payouts. The only payout that's visible on-chain is the final one, in which the money is finally dispersed. And there we benefit from the payout privacy that I described previously. We can push the confidentiality of our Mixicle construction even further. You may have noticed that there are still some confidentiality issues. And in particular, the Oracle must know the trigger on which the Mixicle is based. It, after all, is responsible for implementing the secret trigger code. Ideally, Alice and Bob would like to be able to hide the trigger from even the Oracle itself. Now, this may seem hard to do, but you've actually already seen the solution to this problem in the previous talk. Alice and Bob can make use of Deco. So as you recall, Deco allows a user to prove things about a TLS session to an Oracle. So the setup here is that Alice and Bob commit in the smart contract to the trigger that they're going to use, and then the event occurs, the date on which they want to assess the movement of the stock, for instance, occurs, and then one of the two players queries a website, gets the stock price, and proves to the Oracle that the stock moved in a particular direction without revealing what the stock ticker was, just revealing, or just proving rather, that the stock that the player is querying from the target website is identical with the stock that was committed to in the smart contract. So all the Oracle knows is that Alice and Bob agreed that the trigger was XYZ, and that a player is using Deco to report on the movement of stock XYZ, but the Oracle has no idea what stock XYZ is. That's the idea. So now we're able to hide the trigger from the Oracle. I also mentioned that we'd like to achieve auditability in our Mixicle constructions. And the way to do this is very simple. The players commit ciphertexts on the secret terms of the contract, on all of the secret parameters of the contract to the smart contract itself. This serves two purposes. First, it allows selective disclosure of information about the trade in which Alice and Bob engaged to an auditor or a regulator. it also serves the purpose of holding the oracle accountable. If the oracle cheats and provides an incorrect input, well, there's a record on chain of what it was supposed to do. If the oracle has agreed to the ciphertext terms here, it can then be called out by Alice and Bob, who can decrypt the trigger in the trigger code to show that the oracle provided an incorrect report. The construction in the previous literature, most similar to mixicles, was a very nice idea from Taj Draya, proposed in 2017, called discrete logs. And discrete there is not misspelled, discrete in the sense of confidential. The idea is very simple. The players, Alice and Bob, for instance, partially pre-sign transactions corresponding to all the possible event outcomes in the financial instrument that they are parties to. By partially signed, what I mean is that a partially signed transaction needs some additional signature in order to be complete, in order to be valid as a transaction. Where does this partial signature come from to complete a transaction? Well, in the discrete log construction, Oracle broadcasts a signature on the actual event that has occurred, on the actual outcome, broadcasts a signature S sub j. So the winning player then can take the partial transaction that corresponds to the actual outcome, combine it with the Oracle signature, and get a fully valid transaction, which can then be processed on chain. This is quite nice. And in fact, discrete logs achieves potentially stronger confidentiality than mixicles. Right? The Oracle's broadcasting this signature. It doesn't actually know that Alice and Bob are using the signature in a financial instrument. The transaction that gets processed on chain looks like an ordinary transaction. There's no evidence that it derived from a financial instrument. So you get very strong confidentiality in this sense. But there's a catch, or a few catches. One is that discrete logs are directed mainly at Bitcoin, and in particular Lightning Network. They assume Schnorr signatures, which haven't yet rolled out, and perhaps most seriously, they need this special purpose beacon infrastructure for all possible triggers of interest. For example, you can't achieve custom triggers. But they remain a nice point in the design space for decentralized financial instruments. You can add some other bells and whistles to mixicles. For instance, you can achieve even better payout privacy by combining mixicles with a system that conceals transaction amounts. Aztec and Zether are a couple of examples of such systems. They can be integrated fairly straightforwardly into mixicles at the cost, of course, of more expensive gas per transaction and additional complexity and trust assumptions, which are to some extent at odds with the design goals of mixicles. We can also create non-binary mixicles. We can have mixicles with multiple event outcomes, and we can even conceal the number of possible event outcomes. We can conceal the cardinality of the instrument. We can have multiple players. There's no reason to restrict ourselves to two. And additionally, in an update to the paper we should be releasing 2, we explore a stealth version that's sort of like discrete logs for Ethereum. We actually have a couple of different variants, one that uses ECDSA and one that relies on Schnorr, should it be, or Schnorr signatures should they be implemented. Well, I mentioned that mixicles, because they're conceptually simple, lend themselves to fairly straightforward implementation. And in fact, we have a prototype of the multi-round version of mixicles that I showed you, something we call SIMI-PPS. You'll find it in the paper. This implementation required only 188 lines of code. It's really rather compact and fairly easy to audit, we hope. The gas costs for this transaction, this construction in Ethereum, are also fairly reasonable. The most important cost in a multi-round mixicle is the new round, the cost of implementing a new round here. All the rest can be amortized across rounds. And so this is on the order of 170,000 gas. According to a back-of-the-envelope calculation I did this morning for a standard Ethereum transaction, standard speed Ethereum transaction, this would cost about 13 cents. And as I said, the rest can be amortized across transactions. More generally, though, mixicles are just one point in a large design space for DeFi instruments. And they may need some modification to address real-world needs. I see mixicles as most important in highlighting that oracles can do more than just deliver data, and that blockchain trust and resource boundaries can be flexible, a notion that we see, for instance, in layer 2 systems. To illustrate this, let me explain that when an oracle is invoked by a smart contract, what's called upon is generally not a single entity, but rather an oracle network, a decentralized oracle network. This means that the creators of the smart contract make use of some network, Chainlink would be an example, by selecting a subset of nodes that they particularly trust, a subset of nodes that they regard as reputable or trustworthy. And this subset of nodes effectively forms a permissioned committee, and therefore a high-trust committee. If you have a trustworthy committee, there's a lot you can do. This committee can achieve consensus on the value of some piece of data. That's the basic Oracle functionality that most people are familiar with. But it can do a lot more as well. For example, the committee can facilitate bidirectional communication. It can enable a smart contract to control, say, a cyber-physical system, an autonomous vehicle or a smart lock or what have you. It can do privacy-preserving computation, multi-party computation, for instance, or it can use trusted execution environments. And it can, in principle, even deliver persistent services, things like robust storage. In general, then, this type of committee, and therefore Oracle networks, can empower smart contracts to do a wide range of things that they can't do in an isolated environment. That's it for the talk. If you're interested in learning more, there's a paper online at the URL given here. Our prototype is also available on GitHub. And let me briefly take the opportunity to call out my co-authors here. You see their names, and particularly Lorenz Breidenbach, who contributed some of the key ideas in the paper and did the implementation for the most part, and so on and so forth. Thank you.
Any questions, Ari? I have a quick question. When do you expect this to be up so that people can start experimenting with mixicles?
Yeah, they can experiment with the prototype code.
Okay.
It's available.
So it's functioning.
Yeah.
A question. I know like this Oracle network can verify the truth of the data, but sometimes the truth may be manipulated. For example, a stable coin may be pushed to $2 price temporarily, right? So how would your Oracle network, make sure a stable coin has a stable price?
Well, Oracle attestations are only as good as the proofs that the Oracle nodes are relying on. So an Oracle network can't fix a buggy proof.
Okay.
Yeah.
Hi, so are the gas cost estimates, is that for the version that does use DECO or without?
That's not using DECO, but DECO actually operates off-chain, so it's not going to have an impact on gas costs.
Oh, okay, because I thought somehow with DECO there's some snark verification in the
Yeah,
contract.
that happens off-chain. So.
Oh, really?
Yeah.
Okay.
Yeah, right. So the prover is proving something to an Oracle node, which then relays an attestation to the blockchain. But the proof itself is happening off-chain.
Ah, okay, so you, all right, I see.
Yeah.
Do you have a sense of how the gas costs will scale with additional parties or additional conditions, more complex conditions? For the setup at least?
Yeah, I don't actually know offhand. I'd have to think about it, or we would have to enhance the prototype. I can't give you an answer right off the cuff.
In case the oracle's available for that particular second for contact, and the available oracle is malicious, then how does the network respond? Is the network able to identify?
Yeah, so the concern about malicious oracles is the reason for using a committee rather than a single node. And the presumption is that a majority of the nodes in the committee are going to be honest if you've selected well. This is why you have redundancy. Nodes can fail, nodes can provide false reports.
Let's thank Ari again.
Okay, thank you.
And we are resuming tomorrow at 9.